Good morning and welcome to this lesson. The lesson for today is measures of variation. My name is Eunice Frimpong and I'll take you through this lesson. Measures of central tendency describe where the center of a data set is, as we saw in the case of mean, median, and mode. However, the center alone does not tell us how the observations are distributed around it. Let's take these two data sets. Data set A, it has data points 48, 49, 50, 51, 52, with a mean of 50. Data set B has data points 10, 30, 50, 70, 90, with a mean of 50. Both data sets have the same mean, but are they equally consistent? Now, why do we need to measure variation? Even though we may have two data sets that have the same meaning, like we saw in the previous slide, the first data set is concentrated close to 50, which is the mean, while the second data set here is much more widely spread. You can see that for the first data set, apart from 50, the other numbers are 49, 48, which are close to 50, and 51, 52, also close to 50. But for this second data, apart from 50, we have 10 and 30. 10 is quite far from 50. Again, 90 is quite far from 50. So the second data is more widely dispersed or spread apart than the first data set, although they have the same mean. So the main idea is that the measures of variation describe how far the observations tend to spread from one another, or from the center of the distribution, or from the mean. So in conclusion, a measure of center should usually be reported together with a measure of variation to have more meaning into the data. So what then is a measure of variation? We also call them measures of dispersion. Now they describe how spread out or clustered the observations are. The measures to be considered in this lecture are the range, the variance, and the standard deviation. Now, a small measure of variation indicates that observations are relatively close together, and a large measure of variation indicates that observations are more widely apart. Suppose two classes both have a mean score of 70. What does that mean? For class A, most students scored between 68 and 72. Now for class B, students scored between 35 and 95. However, for both classes, the mean score is 70. What do we observe? They have the same center or the same mean, but class A has small variation and class B has large variation. Class A have more consistent scores, but class B has less consistent scores. So the mean alone cannot distinguish between these two classes. If you are using just the mean, you would notice that they have the same mean. So you cannot put a proper distinction to the two classes. But when you introduce a variation, then you can realize that class A has smaller variation as compared to class B. Let's go look at the range now. Now, the range is the difference between the largest and the smallest observation in a data set. So in simple formula forms, we have range is equal to maximum value minus minimum value. Therefore, once you can identify the maximum value and the smallest value in your data set, you can find your range. The range measures the total distance from the smallest observation to the largest observation. How do we calculate the range? Find the largest number, find the smallest number, then find the difference between the two numbers. So for example, look at this set of numbers. We have 3. We have 3, 7, 9, 12, and 15. The smallest value is 3, the biggest is 5. So the range is simply taking 3 out of 15 to get 12. Another example, a student records the number of hours slept over 7 nights. These are the values: 6, the first night, 6 hours, 7.5 hours, 6.5 hours, 8 hours, 7 hours, 9 hours, 6 hours. From this observations, the largest observation is 9 hours, and then the smallest is 6. So the range is the difference between the maximum and the minimum, which is 9 minus 3 equals 9 minus 6 equals 3. What does this mean? The student's sleep duration varied by up to 3 hours during the week. So the range does not mean the students change sleep duration by exactly 3 hours every day. It simply measures the difference between the largest and the smallest observation. A group of students obtained the following marks in a quiz: 3, 5, 6, 8, 7, 4, and 6. What is the range? Minimum value here is 3. Maximum is 8. So the range is maximum minus minimum. 8 minus 3 giving us 5. Now consider the following data sets. We have data set A and data set B. Set A has a range of 10 minus 6 equals 4, and set B has range of 14 minus 2 equals 12. Therefore, we say that data set B has the greater spread according to the range. So according to the range, because data set B has a bigger number for the range, we say that it has the greater spread. Now consider the data sets A and B. For both data sets, they have the same range, which is 8. For data set A, minimum number is 1, maximum is 9. For B, minimum number is 1, maximum is 9. So they each have the same range. However, the middle observations are distributed differently. But we see that the middle observations are distributed differently. For the A, the numbers in the middle are 555. They are almost the same. I mean, they are the same numbers. But for B, the numbers are different. So even though they have the same range, they are not distributed the same. This gives us insights into one limitation of the range. Two data sets can have the same range, even though the observations between the minimum and the maximum are arranged very differently. So the fact that you see that two data sets have the same range does not mean that they have the same observations. Now consider 10, 11, 12, 13, and 14. Its range is 40 minus 10 equals 4. Replace 14 with 50, okay? So the last number here, we are changing it to 50. The new range is 50 minus 10 equals 40. Therefore, the range is very sensitive to extreme values because its value depends on the minimum and the maximum observations. As you can see, as soon as we change the maximum value to a different number, which is quite bigger, the range also changed. So for the range, when we look at the strength, it's easy to understand. It's quick to calculate. It uses the original unit of measurement, and it provides an immediate indication of spread. But for its limitations, it uses only two observations. It ignores all values that are between the two extremes, and it's highly affected by outliers, especially if the outliers are part of the minimum or the maximum value. And then they can change substantially from sample to sample. Here is a practice example. Calculate and interpret the range of each data set. Daily temperatures, internet download speeds, and a number of support tickets. So for the first one, you have to know the minimum value, the maximum value. So you want to know the maximum value, the minimum, and then the range. For daily temperatures, the maximum is, ideally, this data set should be arranged in order. So let's arrange this in order. We have the smallest number here is 26, 27, 28, 29, 30, 31, 33. So the maximum number here is 33 and the minimum is 26. Therefore, the range is 33 minus 26 equals 7. Now for internet downloads, first number is 14 to 15 to 18 to 20, 22, 25. So for this, the maximum number is 25, minimum is 14. The range is 25 minus 14, and we have 11. Finally, for the number of support tickets, the numbers are the same. So the minimum number is 4, maximum is 4, range is 4 minus 4 equals 0. So it has no range, actually. Now, what does a range of 0 tell us about a data set? It means that there is absolutely no variation in the data set. As you can see, all the observations are the same. So you don't have any variation at all in the data sets. However, for data sets 1 and 2, the internet downloads has more variation because it has range of 11 as compared to daily temperatures with a range of 7. Let's find an error. A student calculates the range of this data set as follows. 15 minus 8 equals 7. What did the student do incorrectly? Well, I notice here that the students found the maximum number correctly, which is 15. However, the students wrongly decided on the minimum number to be 8 instead of 6. I am thinking that very likely the students did not arrange the data sets in order. If you just look at it without arranging in order, you may miss out on either the maximum or the correct minimum number. So rather than using 6, they used 8 and gave us a wrong value for range. So the correct observation is that the smaller number is 6. Therefore, the correct range should be 15 minus 6 equals to 9. So these are the key points to consider when working with range. Here are some questions to give thought to. And here is an example. There is a data set here of staff of a company, XYZ company, and these are salaries of the staff. So the owner all the way to worker 3. The highest salary is 100,000. The lowest is 15,000. So we have, in fact, I almost considered 18,000 to be the lowest salary because it was the last number. But once again, it's very important to observe all the data points and arrange them in order. Actually, there's a 15,000 here. So if you were just looking at the flow and seeing that 100,000, 40,000, 30, you may simply skip this and say that 18,000 is the smallest. So here the highest is 100,000, smallest is 15,000. The difference is 100,000 minus 15,000, giving us 85,000. Therefore, the range does not tell us how the remaining salaries are distributed between 15 and 100,000. It just makes us know that the difference between the highest paid and the lowest paid is 85,000. Now, this motivates the use of variance and standard deviation because the range uses only the maximum and the minimum value, but the variance and standard deviation use all observations within the data set. So what is variance? Variance measures the average squared distance of the observations from their mean. And the standard deviation is simply the positive square root of the variance. The variance is measured in squared units, while standard deviation is measured in the same units as the original data. Why are these measures important? Now, the variance and the standard deviation help us to measure how far each observation tends to lie from the mean, and it helps us to compare the consistency of two data sets. It, it identifies data sets that have high or low variability. It uses every observation in measuring the spread, and it supports more advanced statistical analysis. So a small standard deviation, once again, as we saw in the range, indicates that observations are clustered or they are close to the mean. And a large standard deviation indicates that the observations are spread farther from the mean. Now, here are the notations. For population mean, we use the mu. This is the Greek letter mu. Population variance, we use sigma squared. And population standard deviation, we use sigma. All these are Greek letters that are used to represent mean generally in mathematics, and more so in this course. Now, for sample mean, we have x bar, sample variance, we have s squared, and then sample standard deviation, we have s. Normally, we use n minus 1 in the denominator when calculating the variance of a sample. So, sample variance formula. Now, for any observations x1, x2, all the way to xn, the sample variance is s squared equals the summation of x1 minus x bar all squared all over n minus 1. So in defining the variables in there, xi is an individual observation, x bar is the sample mean, n is the sample size, and xi minus x bar is the deviation from the mean. Once the sample variance has been calculated, we have s equals square root of x squared. You just find the square root of the variance and to find the standard deviation. So the standard deviation is not a separate calculation you do on its own. The most important is to find the variance. Once you find the variance, you can find the standard deviation by finding the square roots, the positive square roots of the variance. So suppose x squared is equal to 16, then we say that s, which is the standard deviation, is the square root of 16, and that's equal to 4. Why do we square the deviations then according to the definition of variance? The deviations from the mean may be positive, negative, or 0. So for example, you may have the following as the deviations: -4, -2, 0, 2, and 4. If you simply sum them, for this particular data set, you realize that when you just sum the observations raw like that, you get 0. And if we simply average the deviations, we are getting the positive and negative values are canceling out. That is why we're getting the 0. So we square them first. Once you square negative 4 squared is 16. Negative 2 squared is 4. So when you square all the observations, you make them all non-negative. They all become non-negative. Therefore, when you sum them, you will not get 0. You get a positive number. Then you can further go ahead square roots to find the standard deviation. Now, these are the steps for finding the sample variance. First of all, you calculate the sample mean x bar, then you subtract the mean from the observations, then you square each deviation, add the squared deviations, and then divide by n minus 1. So the formula here is this: s squared equals summation of xi minus x bar all square all over n minus 1. And we have our s being equals the square root of s squared. Now, we are going to focus on sample variance, not population variance, because generally, whenever we are working with these data sets, we are assuming to be working with a sample. We cannot get an entire population of data sets to work with. That will be a lot of data sets. So every observation we are using to learn, using to solve examples, using to write our test, they are all going to be samples. That is why we are using sample variance and not population variance. Now, there's also a much computationally friendly formula. So the formula we saw here can be broken down into this formula where we have s squared equals n times summation of xi squared minus summation of xi all squared all over n times n minus 1, or s squared equals summation of xi minus summation of xi squared all over n minus 1. They are the same. Whether you use this or this or this, you have the same answer. Now, the shortcut formula is convenient, mostly when you have summation of xi and summation of xi are easy, when these two are easy to calculate. Here's an example. Find the sample variance and standard deviation of 6, 8, 10, 12, and 14. Now, first of all, we know that our n is equal to 5 because there are 5 data points here. X bar is equal to 50 over 5, which is equal to 10. All right, so because we got 50 over 5 because when you sum these data points, you get 15. 6 plus 8 plus 10 plus 12 plus 14 is 50. 14 plus 6 is 20. 20, 10. Yes, so it's 50. So 50 over 5 is 10, which gives us the mean. Now, according to the formula, we have we are using this formula: summation of xi minus x bar all squared over n minus 1. So the formula we are using for the variance is summation of xi minus x bar all squared over n minus 1. Therefore, now that we know our x bar, according to the formula, we need to find xi minus x bar. So we take all our x's, we create a column named xi minus x bar, then we start. X bar is 50. So 6 minus 50 is negative 4. 8 minus 50 is negative 2. 10 minus Sorry, X bar is 10, not 50. X bar is 10. So we have 6 minus 10 is negative 4. 8 minus 10 is minus 2. 10 minus 10 is 0. 12 minus 10 is 2. 14 minus 10 is 4. Now let's square. This column says xi minus x bar all squared. So you're going to square all the columns. You're going to square all the items in column 2. So minus 4 all square is 16. Minus 2 square is 4. 0 square is 0. 2 square is 4. And 4 square is 16. When you sum everything here, you're getting 40. So therefore, the summation of xi minus x bar all square is 40. So we just come to fix this into the formula. We have here 40 all over n is 5, so 5 minus 1. So 40 over 5 minus 1, which we have here. 40 over 5 minus 1. Now we have more 40 over 4, and then further we have is equal to 10. So the sample variance x squared is equal to 10. To find the sample standard deviation is simply s equals square root of 10, and that's approximately 3.16. Therefore, the observations typically differ from the mean by about 3.16 units. Now, let's use the shortcuts formula. So for the data 6, 8, 10, 12, and 14, we have n is equal to 5. We're using the same data as the previous slide. N equals 5, and then summation of xi equals 50. Now, according to the shortcut formula, we have it written here, s squared equals n times whatever we have here. So we can see that we need summation of xi. What does that mean? It means that you're going to take each of the x's and square them. So 6 squared is 36. The two lanes I'm comparing are this one and this one. So 6 squared is 36, 8 squared is 64, 10 squared is 100, 12 squared is 144, 14 squared is 196. You sum everything to get 540. Therefore, we've been able to find summation of x squared, which is here, this one. Now, after that, we can just go into the formula. N is equal to 5. Summation of x squared, we have 540. Then this is summation of x all squared. We've already find summation of x. So we want to square everything, okay? That means we're going to do 50 squared. This is different from summation of the squares of the various numbers. So here we squared the entire summation of x, which is 50 squared. So putting everything into the formula, we have n equal to 5. Summation of x squared is 540 minus summation of x all squared, which is 50 squared, all over n, which is 5, times n minus 1, which is 4. When we further do the computation, we have 2007 minus 2005 over 20, and that's 200 over 20, and that's 10. So the variance is 10, as we saw in the previous slide. And then we have the square root of 10, giving us approximately 3.16 as the standard deviation, as we saw in the previous slide. So we've just shown that whichever formula you use, you will get the same answer. So this gives us 3.16. We have 3.16 here too, using the first formula. Okay. So the value we had for standard deviation means that the observations typically lie approximately 3.16 units away from the mean. Therefore, the standard deviation is not necessarily the exact distance of each and every observation from the mean. It's just a summary measure of the overall spread. Now, here's an example. The daily sales in units for a local shop over 6 days are given as this. Find the range, the sample mean, sample variance, and sample standard deviation. So I've brought it here. This is the data we've been given. First of all, we're supposed to find the range. According to this data point, the highest value is 20. The lowest is 10. You should arrange it in order before you start. So please take note. So let me do that now. The lowest value, let's start. So we have 10. The next number is 12. Then we have 13. Then we have 15, 17, and then 20. So highest number is 20, lowest is 10. 20 minus 10 is 10. Now, we found our range. The next thing is to find the sample variance. We know our n is 6. 1, 2, 3, 4, 5, 6. So n is equal to 6. Summation of xi is equal to 87. When you sum the various x values, you should get 87. Summation of xi squared. So you square each of the data points. You square 12 to get 144. You square 155. You square 10. After squaring everything, when you add it, you get 1327. Then you find your x bar. Your x bar is your summation of x over n. So we have 87 over 6 giving us 14.5. So we come back into our formula and then we fix the values in there. N is 6, summation of x squared is 1327, minus summation of x all squared, which is 87 squared, all over n, which is 6, times n minus 1, which is 5. Simplify to get your final answer, given as 13.1. So that's the sample variance x squared. The sample standard deviation S is given as the square root of 13.1, which is 3.62. So we have our range to be given as 10, sample variance 13.1, and then sample standard deviation is 3.62. Remember that to find the summation of x squared, you have to square each and every data point. We have 10 squared to be 100, 12 squared is 144, 13 squared is 169, 15 squared is, 225, yeah. 15 squared is 225, 17 squared is 289, and then 20 squared is 400. So you sum all these numbers, you should get 1327. What if we have a grouped data? So for group data, each class midpoint XM represents the observation within that class. Because we do not have access to the actual data points, we will use the class midpoints as the observations. And we know that the estimated mean from a group data is summation of fx all over summation of f. So the estimated sample variance is given as s squared equals summation of fx squared minus summation of fx all squared over n all over n minus 1, where n is equal to the summation of f. F is your frequency. So the group sample variance may also be written as this. And then the standard deviation S equals the square root of x squared. And because the class midpoints are used in place of the exact observations, the group variance and standard deviation are considered as estimates. Example, consider the following frequency distribution. We have the class interval and the frequencies. Find the estimated mean, the estimated sample variance, and the estimated standard deviation. Before we go into the solution, let me mention that it's not possible to find the range of a group data. That is why I did not even talk about it. to find the range, you need the actual data point to know the minimum and the maximum. But for the group data, you don't know the actual data point, so you cannot find the minimum and the maximum. That is why you cannot find the range of a grouped data set. Okay, so we have the data giving us this. This is the class interval and the frequency. When you come here, the first two columns here, this is what we have. The question gave us the class interval and the frequency. Now, mhm, okay. First of all, we need the estimated mean. So the estimated mean is x bar equals summation of fx over summation of f. N is equal to 20, which is summation of f. Now we have our x's, that's the midpoints. We found the midpoints of each of the class intervals. Fx is simply the frequency times the x. So 2 times 2 gives you 4. 3 times 7 is 21. 7 times 12 is 84, and all the way to the last number. So after finding the f times the x's, you sum all of them because you also need the summation of f times x. So now that we have the summation of f, which is n summation of f times x, we can find the mean. X bar equals summation of f times x over summation of f, 255 over 20, giving us 12.75. So the mean is 12.75. But according to the formula, apart from the mean, you also need the summation of f times x squared. So this one, the thing is, you first of all square x, multiply by f, then you sum everything. So if you come back to the table, you see that we have it here. Ideally, you should create an x squared column. So ideally, in creating this table, you should create an x squared column first. So we have our x squared as these are the x values, okay? So we have 2 squared as 4, 7 squared, 49, 12 squared, 144. So you do all your x squares like that. Then you multiply by the x square by the frequency. So let me finish the x squared. 17 times 17 gives us 289. Then 22 times 22 gives us 484. So in total, I mean, we don't even need the total for this one. The next thing, how did we get this for f times x squared? We multiply the frequency by the x squared. So for the first row, 2 times this 2 times this 4 gives us 8. That's what we have here. Okay. Then we have next 3 times 49. We have here 147. Then 7 times 144. Which is 1008. So that's what we have. We have f times x squared like that, and then we do for everything. We have to do this because we need the summation of f times x squared according to the formula. So the total gives us 3865 for this column. And when you come here, you just fix the values into the formula. So summation of fx squared, we have 3865. Summation of fx was 255. So 255 all squared, all over n, which is 20. Now everything over 20, n minus 1, which is 20 minus 1, that is 19. So you simplify to get 3251.25. That is, no, this is we took just this part, 255 squared over 20 gave us this. So therefore, s squared is 3865 minus 3251.25 all over 19. In fact, from this point, you are just solving it algebraically. So whatever process you want to go through to get your final answer, please do. We have x squared is equals to 613.75 all over 19. Then approximately our variance, sample variance is 32.30. and the sample standard deviation is the square root of 32.30, which is 5.68. So take note, the expressions summation of xi squared and summation of x all squared are not the same. The summation of xi, you first of all square each observation, then you add. You first of all square each observation, then you add. But for this, you first of all add the observations, then you square. You first of all add the observations, then you square. So that's the difference. The final thing we want to look at is the coefficient of variation. The coefficient of variation is a relative measure of dispersion. So for example, the coefficient of variation is given as the standard deviation over the mean times 100%. And for a population, it's given as the population standard deviation over the population mean times 100%. So how do we interpret this? The coefficient of variation expresses the standard deviation as a percentage of the mean. So this is a step ahead of the standard deviation. Now let's look at it. Why should we use coefficients of variation? It's useful when you are comparing data sets that have different means. You realize that for the data sets that have the same mean, the standard deviation can be a good measure of distinction. But what if the data sets have different means and you calculate their standard deviation? It will not be so clear the difference between the two data sets in terms of their variation. But the coefficient of variation helps us to know to compare data sets even when they have different means. You can also compare quantities measured in different units. It helps to assess the relative consistency of two different data sets and then comparing risks or fluctuations relative to the average size. So the head and tail of coefficient of variation, the main thing here is that once you have more than one data set and you want to compare, the coefficient of variation becomes very, very useful. So the standard deviation measures the absolute variation. It gives you the variation in a particular data set. But then the coefficient of variation measures the relative variation. That is, it gives you the variation in one data set as compared to another data set. So a standard deviation of 5 may be small relative to a mean of 100, but big relative to a mean of 10. Therefore, the size of the standard deviation should sometimes be considered relative to the mean, right? So when it comes to the coefficient of variation, it helps you compare the standard deviation even within one data set. It helps you to compare its standard deviation against its mean. So let's look at an example. You have two data sets. We have car sales and we have commission. The mean of the car sales is 87 and the standard deviation is 5. For commission, the mean is 5225 and the standard deviation is 773. Determine which variable is relatively more consistent. If you look at just the mean and the standard deviation, it's not easy to just determine because they have different means and different standard deviation. So if you want to know which one is more consistent, we can use the coefficient of variation. When we consider car sales, the coefficient of variation is given as a standard deviation over the mean times 100%. So we have 5 over 87 times 100%, which is 5.747%, or approximately 5.75%. For commission, the coefficient of variation is equal to the mean over the standard deviation over the mean, which is 773 over 5225 times 100%. That's giving us approximately 14.79%. Therefore, the CV for car sales is 5.75%, and the CV for commission is 14.79%. In conclusion, Since 5.75 is less than 14.79, we say that car sales are relatively more consistent because they have the smaller coefficient of variation. Car sales are more consistent because they have smaller coefficient of variation as compared to commission. Another example, we have two servers, server A and server B. The mean of server A is, so the question is what I'm focused on now. Okay. So this is the question. The mean for server A is 12 minutes. The standard deviation is 3.6. Now for server B, the mean is 40 minutes. We are looking at for each server, the downtime for each server, okay? So the mean downtime for server B is 40 minutes, and then the standard deviation is 6.8 minutes. The question is, determine which server is more consistent. So we can use the coefficient of variation. So the CV of A is its mean, its standard deviation over its mean, 3.6 over 12 times 100%, which is 30%. And then for server B, we have its standard deviation over its mean, which is 6.8 over 40 times 100%, and that's 17%. So CV of B is 17%. Now, since 17% is less than 30%, we say that, and the 70% is for server B, we say server B is more consistent. Now, although you notice that although server B has a higher average downtime of 40 minutes, its downtime is more consistent because it has the smaller coefficient of variation. So consistency is not the same as performance, right? Yeah. A lower CV indicates that the greater consistency, not necessarily better performance. Here's another example. The mean download speed in region X is 80 Mbps with a standard deviation of 10 Mbps. The mean download speed in region Y is 50 Mbps with a standard deviation of 5 Mbps. Calculate the coefficient of variation of each region and determine which region has more consistent internet speed. All right, so let's look at region X. Region X. And then this is region Y. We have the mean. Oh, let me use the notations. The mean is giving us X bar. Standard deviation is S. So the mean is for region X is 80 with standard deviation of 10. Here the mean is 50, standard deviation of 5. So then the coefficient of variation for region X is the standard deviation over the mean, 10 over 80, which is 0.125. Then for region Y, we have 5 over 50, which is 0.1, 0.10. So we see that 0.10 is less than 0.125. Therefore, because region Y has a lower coefficient of variation, we say that region Y is more consistent. Right. Okay. Now, here's another example. Two applications have the following response times. App A has mean of 120 and then standard deviation of 15. App B has mean of 90 and then the standard deviation of 18. Calculate the coefficients of variation for each application and which application has more consistent response time. Please do this and then share your response. Another example. Two students record time required to complete assignments. The data is given as such. Determine which student is more consistent. Practice this and give us your response. When should the CV be used carefully? The coefficient of variation should be interpreted carefully when the mean is 0. When the mean is very close to 0, values may be negative or the measurement scale has no meaningful 0 points. Because the coefficient of variation divides the mean, a very small 0 mean can make the result unstable or undefined. Now, here is a summary of the measures of variation we have looked at. We looked at the range, which is the distance between the maximum and the minimum value. It uses only 2 observations. The variance is the average squared spread around the mean, and it's measured in squared units. Standard deviation is the typical spread around the mean, and it uses the original data unit. And then finally, the coefficient of variation is a standard deviation relative to the mean. It's useful for relative comparison. These are the key formulas.